Hello everyone, today we're going to be doing a tutorial with Vivado on how to implement your IP, whether it be a Verilog or VHDL file, into an AXI port so that you can use it within your design for testing, specifically in this case for Xilinx products, particularly the PYNQ Z1 is the one I worked with, but this should work in general with other PYNQ systems and other Xilinx-based boards. So this video comes out of necessarily trying to figure out how to implement my IP, which I wrote in Verilog, and trying to implement it in hardware. If you don't decide to use Vivado HLS that's packaged with Vivado, it becomes quite easily a little bit difficult to figure out how do I implement my IP, how can I test it, and how can I extract my data. So in this tutorial we're going to be showing how I overcame that. Granted, that may not work for everyone, but this gives you a general idea of what you can do and the options you have as to how to troubleshoot, how can I get my IP into a hardware design and to get it running as well. So the first thing we're going to do is we're going to open up Vivado here and we're going to create a project. So once you have the project creator open, you can give it a project name. For the purpose of this video, we're just going to go ahead and call it hardware, let's call it hardware custom. Why not? Hardware_custom. You can change your directory, but we're not going to do that. I already know where it's going to go. And then you're just going to leave it as an RTL project. You're going to find the board that you want to work with. For me, I'm working with the PYNQ Z1 board, so we'll select that, and we will finish. So once this is done, wait for this to load. Once we're done here, we'll get obviously the blank Vivado just kind of home interface screen. We're going to create a block design under IP integrator on the left. We'll call it whatever we want to do. So we're going to call it just new hardware, new_hardware. I accidentally hit caps lock, but don't worry about that. Just new hardware. And we'll create a block design. So one thing we want to do right now before we forget is we are going to go to the new hardware up here. We're going to right click it. And we are going to go to we're not even there yet, so don't disregard that. We'll come back to that. But first thing we're going to do is right click over here in this blank design area. We're going to add IP. So we're going to go search for the Zinc system if you're using a Zinc based processing system. If you're using something else within the Xilinx line, I don't know exactly if it will work for this case or not, but we're using a Zinc based system, so we'll use that. We'll run the block automation to set up the DDR and the fixed I/O ports. We're not going to be messing with those, so we'll be totally fine. And then from here on, we're actually going to be able to create our IP. So to do so, we're going to go up into Tools in the top left-hand bar corner, and we're going to go under Create and Package New IP, one of the top options. So here, it'll tell us that we can create and package new IP. So we can create new IP based off of the IP catalog we made. So pretty much using existing IP, we can create a larger piece of IP, or we can create a new AXI4 based peripheral, which is what we're going to do. So clicking next, we have the options of either packaging an IP and creating IP using pre-existing blocks, or we can create an AXI4 peripheral. In this case, we're going to create an AXI4 peripheral. We can call it whatever I want. So we're in this case, since my hardware that I want to design that I made in Verilog was an oscillator, we're just going to call it oscillator design. And you can edit the description, version, IP location, whatever you want to do. Its default is right under your current existing work source, so or work location. So it won't go that far. It's pretty easy to find. So once you're here in the interfaces, this will give you the option to add or remove slave and master ports from your AXI4 design. AXI4 designs, from my understanding, essentially allow data to be moved back and forth while running operations at the same time. So in this case, since my oscillator is outputting data very fast, what we're going to want to do is change the interface type. So the interface type you have between all AXI ports is light, full, and stream. These pretty much determine how much data you can output at a singular time and how fast. Stream does so on a clock-based scale rather quickly, whereas light and full will grab an individual piece of information at a time. The full just has larger bandwidth, but we're just going to be sticking with stream since my data is rather continuous. If you only have one plot point or one data point that's not working in continuous time, you can do light or full. But if you have a continuous system that's outputting data very fast, stick with the stream. So we're going to create a slave stream port, and then just for the sake of it, I actually don't use the slave port in mine, but I will still have it on there. We're going to also create a master port so that we can send data. So the slave port you can use to receive data into your AXI design, and you can use your master to send data. And we're going to make sure they're both stream. We can leave the data bit at the data width at 32 bits. There's no other option. You can change the name of your AXI port if you want. We're just going to leave it as is for the time being, and if you want to enable interrupt support, you can do so. I do not have any knowledge in working with interrupts, but if you do, you can add that if you are interested. But once you have kind of like your basics of what AXI ports you want, whether how many ports you want to output data with, how many ports you want to enter data with, depending on how many slave and master ports, of course, respectively, you can do so. So once you're done adding all the ports that you would like, you just click next, and then we will go into edit IP in the next steps option. So once we click finish here, it'll create the new project for us for our new IP, and it will automatically open up the page for us into the new IP. So right here, we're directed towards the package IP. This pretty much just gives us the information of the IP we have already. As you can see, everything from the get-go just has green checkboxes, which means it's typically just going to work just the way it is. But we want to edit this so we can implement our Verilog or VHDL design. Now, depending on whether you like to have Verilog or VHDL, I believe is embedded within Vivado settings. I believe as of now for me, it's set up just to run Verilog right out the gate, so we'll be working with Verilog. But if we click under the tab here, under your IP design name, so in this case we call it Oscillator Design, and it's version 1.0, as we can see up here. If you click under the tab, it'll show you the slave and master Verilog modules. So to output data, we're going to go into the master port. So we'll just double click on that, and it'll open up the Verilog. So I'll quickly just go over what's in the master module, and as well what's in the slave module, and we'll get to editing. So the first thing within the master module is that it contains two parameters up here. It has the data width, which is 32, and the start count. The start count is essentially just the amount of clock cycles it takes before data is sent. This just lets you know that your data is not going to be output the second you request it. But going down, we have essentially your input ports, which is your clock up here. You have your reset switch. You have, which the reset switch by default is active low. So if you input a 0, it will reset. We also have output wire for validation. The most important one that we are going to be working with is the AXI transfer data, or T data. This essentially is going to be the output that you want to transfer, and then tester be transfer last, transfer ready. But again, the main ones we want to work with are going to be the clock up here, and as well the master AXI data, which we will see. Moving along, this parameter down here is going to be very important. Local param, number of output words. This is the amount of 32-bit words you would like to output. This will determine how much data, if you have a continuous system, you would like to output. So let's say if this is right now the way it is set at 8, it will currently output 8 contiguous words every clock cycle this thing outputs data. So essentially, let's say you have this run, you have something that's running real time, so every clock cycle this thing updates, it'll output 8 words, and then it'll be done with the transfer. So if you would like to have more words, you can do so. In my case, since I want to grab a lot of data from my very fast system, we're just going to leave it at 1,000,000. Then down the road, this has just, it pretty much estimates clog B2. It's just a general log base 2 function to determine how many words or how many steps it needs to do in order to transfer everything. Don't worry about this. Don't worry about any of these local parameters up here. The code itself, though, for the rest of Verilog uses these shortcut words. If you look down here with the assign, you can see what keywords that they use instead, or what they're used for. Essentially, they're just kind of filler words using different wires. So this is just something to note about when you decide to work through it. So most of this right here, as you can see, control state machine implementation. That just pretty much just keeps everything running, and you don't really have to worry about anything until you really get down all the way down to the FIFO read enable generation. This is on default line 207, repeat 207, and this is essentially where our data is going to be output, and this is what we care about. Everything else is just making sure everything works just as fine as a general AXI module. What we care about is our output data. So right now, if it's on active low, it just outputs a single one, whereas if TX enable, or essentially the transaction enable, is on, if the transaction enable is on, which pretty much just means that it's ready to transfer data, it'll output the stream out data, which right now is just at essentially just a 1-bit increment counter. So just go 1, 2, 3, 4, 5, 6, 7, 8 by default. However, it will change given that you change the amount of words in which you put as stream data out. This will be important essentially for determining what the master port outputs and the data you want as well. And at the very bottom, it gives you kind of just a general layout of add user logic here, user logic ends here. It's just mostly for your discretion, so you do not mix it up with everything else, but it's not a restriction, it's just a suggestion. So we will be working with that later. The other file we care about is essentially the slave. So as we can see here, slave design, also data width of 32 bits from the data you want to send in. Right here, which I did not discuss in the master port, is user to add ports here. So if you would like to add ports to these AXIs, you can do so, but you are not required to whatsoever. So this also runs on a clock, reset switch, data width, etc. This pretty much just tells you what you're going to get as a data input. It works very similarly to the master port, however, it's essentially just going to receive data from whatever it's connected to. So unless you would like to specifically write something such as in the stream data FIFO down here at the very bottom, then it's not really required for you to change this. This will automatically grab data from whatever you're sending in this case the Zinc 7 system and whatever you call it to send. So it's typically not something you have to worry about, but if you would like to mess with the FIFO built in within the slave AXI, you can do so. I would not recommend it, but it's just there for your discretion. So if we also look up here in the top file within our version 1.0, this is just the general Verilog file for everything that we're using. Essentially, it just creates two different modules. It just creates the slave and the master module. If you add ports, of course, you will have to add that to the module declarations down here. So right here, line 44, instantiation of the slave port, and then 57, instantiation of the master port. So that's at lines 44 and 57. If you add ports, please add them down into the module design for the master port. Starts at line 61, and then 47 for the slave. But beyond that, we're going to actually start by adding our code, which I will make an edit here, and I'll go along with you here in a few seconds. Okay, I have now added essentially my IP, or my Verilog design, within my master AXIs, and I'll show pretty much what I've done, at least within the master AXI port. So I've left pretty much everything the same. I have not added any ports. Again, you can add ports if you need ports for your design, but for the most part, it's not really required to change ports unless you need them. What I have done is, of course, like I showed, I changed the parameter of the number of output words I want to be up to 1 million right now. So it will output 1 million words. Be wary that there is a limit to how many words you can output, and we'll get to that later. Another thing I did was, if I scroll down over to down here actually, so essentially from this line up until this line that you can see highlighted. That, if I can zoom in here real quickly, I guess I cannot. That's an unfortunate bummer. But what I ended up doing was adding my system here. So I added pretty much wires for my design. I implemented my design as a module. However, I have not written the module code, so unfortunately I will show you how to get around that later. But essentially, I instantiated my module, essentially running given parameters. So I implemented the wires I created. So I created a bit cosine wire, a bit sine wire, a 24-bit cosine signal, and a 24-bit sine signal that goes within my design. And I let it run at the same clock the master clock does, which essentially is just the system clock of the entire hardware circuit. So essentially all you have to do is think of this like a test bench, create your wires, and create your module design, and essentially you're pretty much good to go with having this thing ready to run, at least for the most part, of just making sure it exists within your system. The next major change I did make is, like I said earlier, under the FIFO read enable generation. So what I did was under the if transaction enable or TX enable, what I did was instead of just leaving your stream data out as just an increment counter, I erased that and I implemented essentially my own user logic as to what I want output every time a clock cycle goes inside the master port. So what I ended up doing was I said if my cosine leads with ones, because I have a 24-bit output and this is going to be 32-bit and I want to buffer it in so it has a sine signal. So what I did was I said if the top bit is 1, just buffer in the top 8 bits with ones and then just output my signal in the bottom bits, and then otherwise, which means that my top bit of my 24-bit signal is 0, just buffer with zeros up top, and then the bottom 24 is just my signal. Essentially here you can just output whatever data you want into stream data out. Just remember that it is 32-bit by default. I do not know how to change it from a different signal, but this essentially allows you to output data from your module so that you can collect it later. Once you're done writing whatever user code or whatever user logic you want, make sure you press the save file button, which is the little floppy disk up here. You save it, and what this will do actually, which is very convenient, is if it will tell you if there are any compilation errors within your Verilog. If you look to the right over here, there is a little yellow tab here. It's just a warning. It tells you essentially what's going on, and you can click along the wheel. Right now, the only error, or I guess warning, is within this parameter. This parameter always gets a warning. Do not worry about it. Just leave it alone, and just keep on moving on. So once you're done with your master axes and just adding your user logic and what you want as your output data, you can close the tab up here. And then if you want to add anything to your slave axis, you can do so as well. Don't forget to add ports within either your master or slave if you decide to do so. Last thing that you can end up doing is also adding in wires and ports within your top design if you decide to use that. Again, line 20 in the top file, add your ports and then add them within your modules appropriately if you did add some in the first place. Once you're done there, essentially you can close back out and go back into package IP. From there on, we can see here in file groups there is a little file with a pencil icon. Just go to this. If there's other ones, just start from the one most up top. It usually tends to be file groups, but essentially it'll give you a suggestion up here, merge changes with file groups wizard. Click on that, it will run the automation process for it. It will typically check everything else off to be a-okay. And then addressing in memory exists. It gives you the option to add a memory map or an address space for your IP to output something. We don't necessarily need to do it, but for the showcase I'll do so. So in this case, you can choose any of your input ports that input or major output ports that you would like to store as IP. For me, I like to store my master axis with the data I'd like, so I'm just going to highlight this, press next again, and finish, and it will create memory for my master axis port so that this data can be saved and sent over. That's rather important. If you're requesting data from your slave port, I'd recommend by adding another one. You can do so by right-clicking, IP addressing, and memory wizard, and you can go through it again. So in this case, why not? I'll add my slave ports, finish it, and it's done. So this should add both. It looks like it only added one. Oh, add memory map, of course. But anyways, you can change it. So yeah. Once you are done there, you can see it added it up into ports and interfaces. But still, once you are done there, you go into review and package, and it says your IP has been modified. Don't worry about that. We're done there. We're just going to click repackage IP. Quick editor's note. I totally forgot this, but to implement your design, once you instantiate the module within your design, what you need to do is if you look under the master port, or at least I instantiated it, wherever you instantiate it, whatever port, there will be a file, and it'll pretty much be the one that you created. In this case, I left it as oscillator test is what I called it for my oscillator. It'll have a question mark on it since it doesn't know what module it is or where it came from. So to do this, and you can just right click on it, add sources, add or create design sources is what we're going to do. Next, we're going to add a file. For me, I already have this two-phase oscillator that I want to use, and that's the file I want. And we will finish, and it should turn into a blue bubble here. So if I go back into package IP, everything's good. Just merge the file groups, review and package, repackage, and it should be good to go. I apologize for making that error, but we'll get back to the bitstream. So then it'll say finish packaging. Do you want to close the project? Yes, this will allow us to turn to pretty much our base design. So now that we have our IP developed, we can right click again, add IP, and then since we call it oscillator design, if you search it up, it exists now in our IP. So we can double click on it and let it exist now within our system. So great, now we have an AXI stream module. Well, how do you even use an AXI stream modules or AXIs in general? If you're using an AXI stream module, what you'll have to do is you'll have to add a DMA, or a direct memory access port. So what we're going to do is we're going to select AXI direct memory access, and this will allow us to essentially gather the data and store it in memory for us to use. Since we're using AXI stream, it will allow us to create or to collect contiguous data. If you're just using a simple AXI, it will add an AXI interface already within the connection automation, and so you don't have to add a DMA. But if you're using a stream, please add it. Then the designer assistance will be available. We'll run the connection automation. It'll actually just connect the DMA to the rest of the system. From then onwards, we can go into the DMA. We're going to double click the DMA and just remove some unnecessary ports. We don't need this gather engine for at least this purpose. If you have a AXI port that requires it, you can leave it on. And I believe that's about it. Now, going back as to the limit of how much data you can output, this is where this becomes important. So depending on the amount of words you have, depends as well as pretty much how much data you can output at the same time. And the DMA is what's going to hold our data. So this becomes important. So if you look up here towards the middle of the options, we have a width of buffer length register, 8 through 26. And it gives you the choice to see what length buffer you want. And so this pretty much determines how much data you can have. And you can calculate the data you'll get by doing 2 to the however many bits, so essentially how many possible points, and that's how many bits you'll be able to have. If you divide by 1024, that'll give you the amount of kilobytes that you can store. Or you can do the same thing with megabytes, just divide by 1024 again, and it'll tell you the amount of megabytes you can store. If you go up to 26, you can store up to 65 megabytes. It's quite a lot for at least if you're just storing integers, which is fine. Just be aware though that you are using 32-bit words within your AXI peripheral, and each one of those is 4 bytes. So depending on the amount of words you want, you can determine the data you have essentially by multiplying the amount of words times 4 bytes each, and it'll tell you how much data you have. So that becomes quite important into knowing how much data you have, and I believe I said earlier 2 to the whatever bits you have, that's the amount of bits, I'm sorry, that's the amount of bytes, but still, the app still applies. Check the amount of data you have, again, by multiplying words times 4 bytes each for 32-bit, and then determining here how much storage space you have. 26 maxes out, gives you 65 megabytes, it's plenty, it's good for about anything, but if you need less or don't want to use as much, you can lower it down accordingly. So we're going to press OK here. And then one of the latter things in finishing up in the connection design is connecting the ports of your IP design. So what you're going to want to do is you're going to find the stream ports. These will be the AXI S ports labeled on the AXI DMA. So here we have a master AXI S port that goes from master or memory mapped to stream. We're going to connect this one over to the slave port that we have, the slave AXI port, and then as well we're going to be connecting the slave AXI S from stream to memory map. This will allow us to essentially gather our data from the master AXI stream port on our design. So we'll connect those. And then we will connect the clocks of our systems. This will just essentially leave as the system clock. If you have a different clock, you can use that one as well. But we'll be just connecting these as under the general system clock. So let's see if I can connect this up to here. Unfortunately, it does not like me at the moment. I'm selecting the incorrect one. That's why. It's not letting me select the correct wire. But yes, we'll connect this to the clock up here. Let's see. Yep. Connection automation just wanted to connect that. But once you're done connecting these, if you want to connect interrupts, you can connect them here and here on the DMA. And if you have interrupts, you can also connect them on the oscillator. You don't have to set up resets. It should be good to go as is. Now, the last thing, well, you can actually remove resets, or you can input resets as well. If you want to make sure your design has no reset signal, what you can do is you can right click here, add IP, you can go to constant, and you can leave it under as, double click on this, leave it as a 1. We'll just make another copy of this since this is it's active low. You can just connect it with 1s and it should be active all the time, or you can remove the port in and of itself and it should be good to go. But this is what your design should look like, or if you have different AXI ports. Looking at my actual design, which I actually can pop up right here, that is not quite it. Here we go. So this is the actual one I designed, and this one I actually kept in the reset ports, which actually we can get back by doing the following, actually. So if you actually want to use the reset as well, you can also just connect the reset ports up to the reset signal that's found within your AXI interconnect. So just peripheral reset, it'll just allow it to reset with everything else. It's also an option, and we'll just leave it as that. But essentially, from here, your design is pretty much done. You've connected your IP, you've created the AXI port for it, connected it to your DMA, so you can access memory, or directly into the AXI interconnect so that your Zinc system or whatever Xilinx system can work with it. So finishing this up, what we're going to do is we're going to synthesize our design. We're going to press OK. We can change the top module name, and to change the top module, we can go back into sources, and then we can go right click on our hardware block. We can create a HDL wrapper for this. Let Vivado manage this. You know what, this needs to be the top file first, that's why. Okay, let's see if I can do this. Let's see. I am trying to remember how to do this, how to set this up as a top block. I really apologize. So give me 1 second. So to make this a top, I'm sorry, I apologize for this, but to make this a top module, there are some clocks that are not connected within our DMA, unfortunately, which is the MM2S as well. So we have to connect this to the rest of the clock system, something the system did not do very well. You can also change the clocks of these as well if you ever so desire. Just make sure they work appropriately between the systems. In this case, we're just going to leave it with the system clocks, but you can change it to something else. But now we should be able to create a VHDL wrapper, or an HDL wrapper. This will allow us to create this as the top block design, which we need so that we can export this into hardware. So if you look back up here in sources, right now it's a little triangle, and it's now turned into a blue circle. That means it's good for synthesis. So you can run a synthesis, or if you want to output this as to something like on your PYNQ, you can generate bitstream, which will also do a synthesis if not so ready available. So we're going to generate this bitstream, and once it's done, I'll come back to you guys. Okay, so the bitstream is finally done. We can press X or exit, I guess, from there, from that little tab. And then the only other thing you need to do on top of this is you need to go into File, Export, and export your block design so you can create a TCL file. Other than that, you essentially have all the tools ready to go to implement your design and to go test it. Depending on which system you're using, if you're using a PYNQ, you can go to the PYNQ website on how to use an overlay and how to access those files. Otherwise, you can look at other documentation for what other Xilinx system you're working with, but that's essentially how you create your own design, your own IP design based off of Verilog and VHDL, primarily Verilog, but yeah, that teaches you how to use that and also how to set it up with the DMA so you can extract data and record it from there. Again, you can look up how to use the DMA using the appropriate documentation, whether it be from the PYNQ website or whatever system you're running on. But yeah, that's all I have for today. If you have any questions, leave so in the comment section below and I will try to get to your answers. Other than that, have a great day and I hope this helped.